Welcome back to Python with Andrew. And in this workshop, we're going to look at recursion or recursive functions, which is a very strong concept in many programming languages, I should say, especially Python. Recursion is also an interesting one because some people say don't like it at all. Some people say excellent, really good, very powerful. So whether you choose to use it or not becomes more personal preference or depending on the problem you're trying to solve. Now, I'm going to introduce you a couple of examples. One that I think, well, it illustrates recursion, but is it a good example? Probably not. Another one where it's probably a better example of recursion and how it works. Some people just do not like the use of recursion. They say it's inefficient, not good, etc. In fact, I always tell the story of when I was a lot younger and I went for a job. I actually failed a job interview because when they asked me to write a bit of code, I write it using recursion. So it was very nice and pretty, etc. They said, no, don't like that. So we're not giving you the job. So sometimes it pays to decide when you're going to use it based on what other people like. What is recursion? In the simplest form, recursion in terms of a function is just calling the same function again. So instead of doing a while loop, you're calling the function. So inside the function, it calls the function again, and then calls it again, and calls it again. And like a while loop, if you don't have a way of it stopping, it'll keep going forever. Same with recursion. If you don't have a way of stopping it, it will go forever. So in its simple form, it's used to call the same function for, if you like, a sub-element. So when you're doing applications where there's like a tree-like structure or naturally, at this point, we do the same thing again. Either you're going down a tree, looking at different elements of the tree, you want to do the same processing. Or if you think about if we were driving and we go to a corner where there's an intersection, and we make a choice, once we start going and make a choice to go left, for example, we're doing the same process, driving to the next intersection, right? And so we're sort of doing it recursively. So let's pop over and let's have look at a few examples of how we could do this. Okay, so in the simplest sense, I said it's a function that calls itself. So let's define a function. Doesn't matter what it's doing. No parameters. Now, if I was doing this with a while loop, for example, while I is less than 10, print, spelled correctly, while I is less than 10, print I. Okay, if that was my function, and then I called foo, I just made that name up. And if I run that, what do you expect to happen? Well, it's going to go forever because I is always less than 10. So let's ask, actually, I should set I to I equals 0. Okay. So if I run that, and let's see what happens. It should just go forever and ever and ever. And if I don't stop it, it'll keep going forever and ever and ever. So there's nothing of any use there. So let me cancel that. Because normally what we would have is I plus equals 1, right? And that makes more sense. We're incrementing it so that this particular condition gets met. So now if I run that, down the bottom here, 1, 2, 3, 4, 5, 9, stops. Whereas previously the other one just kept going forever and ever and ever. Okay, so nothing fancy about that. And I just use that to illustrate the same could be happening with recursive functions. Often people say recursive functions, you could go forever. Well, of course you could, just like you could with the while loop. So the way we would do recursion, if we just, again, just call foo, again, right, and let's say we first of all, don't need that, we print hello, and then call foo again. Again, there's nothing stopping it, so it should go forever. Okay, so if I try and do that, and in fact, you can see it goes for a long time. The good thing is that Python says, hold on, at about 1,000, I'm going to give up, right? So it actually aborts and says the maximum recursion depth has exceeded, because I think it's about 1,000. I'm sure that's machine dependent, but either way, good, lucky for us that it stopped. That's a good thing because we've got no way of stopping that. So that's just to illustrate recursion is just simply calling itself over and over and over again. But just like a while loop, you better have a terminating position. Otherwise, it'll keep going over and over and over again. So let's look at one of the most famous examples of that what people use to illustrate recursion. And I'm going to copy and paste it. So this is computing the factorial. And in this case, I've done it with a for loop, first of all. So for those that are not familiar, factorial means the factorial 4, for example, is equal to 1 times 2 times 3 times 4. You just go, you keep going up and up and up until you get to the end. And in this case, it would equal 24, I believe. Okay. So that's what factorial 4 is. So you just keep doing over and over again. So in this case, we've just done a for loop for I equals range 1 to the number, and then just keep multiplying by itself and return the results. So now if I print factorial 10, for example, it gives us the answer of 1 times 2 times 3 times 4. Nothing fancy about that. As an aside, for those, I'm cutting and pasting here because I've actually been asking ChatGPT to write all my code for me. I like that. So for these small, short, sharp functions, it's quite useful. You know, I've done a few videos on using tools like ChatGPT to help you code faster and better. And I'm going to do that as much as I can in this particular example. Why not? They're simple functions. They're easily understood. So the factorial version, sorry, the recursive version of this, I'm going to call it R. I'm going to call it rfact, all right? Just capital R, just so you know it's a recursion factorial. And in this case, you'll see I've got the end case. If it's equal to 0, return 1. I could probably do it from 1 and return 1. That might be a little bit better. Otherwise, I'm going to return the number times the function call with 1 less. So I'm going to call the function again, but with 1 less. And sooner or later, it's going to get down to 0 and return 1. Okay, so if I copy this print down, hopefully I should get the right same answer again. Print, in this case, I'm going to do print R factorial 10. If I do that, you'll see that I get the same answer, no surprise. Now, if we did something like, let's print out the number as we go through. So let's just stick a print statement here. Let's print n. And what n should do, it should go from the 10, 9, 8, 7, 6, 5, as it keeps looping through. All right. Remember, this factorial went up to 10. We're going to go down to 1, or down to 0, in fact. So if I change this, you'll see 10, 9, 8, 7, 6, 5, 4. 0, it then says, 0, I'm going to go all the way back and multiply them all as I go back up. So it sort of goes down and then back up. So that's why they call it recursion. Go down, 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 back up. Okay. So that's the sort of base case that people often talk about. And if someone said to me, which is better, I would say, really, it's hard to tell. It's personal preference. Most people would say this one here looks better because intuitively you'd say it's 1 times 2 times 3 times 4, all the way up to 24. So it's probably not a great example of recursion. If you looked at the lines of code, pretty well the same number of lines of code, nothing special there. So if you were to ask me, I would say not a particularly good example of recursion. It illustrates it well and it's nice and simple, but not an example where you say, hold on, it's better than it is. So let me delete that one, here my screen. Let me move on to one that I think is more intuitively like factorial, or like using recursion. And the example I'm going to use, I'm going to copy it over here. If I had a list, right, and I want to sort that list, so it's in a numeric order. Now, there are many, many ways of sorting, and this is not an exercise on how's the best way to sort numbers. I'm going to focus in on one method, which is called the merge sort. And the idea of the merge sort is, if you've got a list of numbers or objects, etc., you cut it in half, and then you work on the first list. And then you cut that one in half and work on the smaller list. Cut it in half. And so you keep cutting it in half until you get down to one number. And then as you go back up, right, you sort of take the left hand that you've cut, the right hand cut, and then you've got 2 sorted lists and you merge them together. So you merge the left with the right. And so it's sort of like cuts it and says, merge this one, and then when you come back, put them together. Okay, so naturally, it is recursive in nature, just the way I'm explaining. Cut it in half and then merge the left, or sort the left and sort the right again and again and again. And eventually, you come back up and you're putting the sorted lists together. Okay. Now, if we were doing this without recursion, now typically there's two functions that you would do with recursion. Sorry, with sorting. First of all, you would sort them, or sort of cut them in half, and then you would like merge them. So you cut them in half, and on the way back up, you merge them. Okay, so and I'm not going to explain the merge together, which is sort of like taking the next number and put it into a new list. Okay, that's a sort of second process. That's not recursion. That's just taking 2 lists and merge them together. What I'm focusing on is, if you like, showing what it looks like if we had 2 functions. So this is the merge sort function without recursion. And what it does is it goes through and goes through 2 loops, right, and continually looks at the left-hand side and works on the left-hand side and then merges them together as we go. That's with the other function. So that's the merge function without recursion. What I want to look at really is the merge function with recursion. So let me see if I can find that. There we go. I want you to compare this. I'm going to call that R merge sort. Okay, so if you look at these 2 functions, and you might want to have to pause the video to investigate these, you'll see the top one does 2 loops going through, whereas what the bottom one does, it says, okay, I've got a list, and if the list is less than 1, right, the length is less than 1, I'm just going to return it because I'm done. I can't sort a 1-element list. Right? Once it gets to 1, I just return it back. Otherwise, I'm going to split it in 2, and I'm going to merge the left and merge the right. Sorry, sort the left and sort the right. So you can see here the lines 27 and 29 to 29, if you like, splits the two lists. And 31 and 32 says, go and sort the left-hand side, the first, and go and sort the last. Okay. And then when we come back, we merge them together using the same merge function as up here with merge. Like I said, that's not the interesting part. The interesting part is the, if you like, the sorting part. Now, to my mind, when I look at the code above here with two loops, I'm trying to think, why has it got two loops and how is it done? Whereas I like here, it's quite simple because I'm saying, I've got a list. If it's got one element, I'm done. If it's got more than one element, I'm going to split it up and I'm going to do this. I'm going to sort the left-hand side. I'm going to sort the right-hand side of my list. When it comes back, I'm going to put them together. So each time it's going down, 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 down to one. And then as it comes back up, it's putting them together, comes back up, it's putting them together, etc., etc., etc. So I think when I look at this list, this one here, if you like, is more intuitive than the one above. Okay. So I'm not going to put the full one there and demonstrate what happens when we run it because it sorts the list. That's quite easy. I just wanted to show you the two different bits of code and then let you decide which you think is better. What's important is that you see how we've done with this recursion. We just sort, if you like, the left and sort the right. So we're making it smaller as we sort, but also the other key part, we better have an end case. If we don't finish it, we don't return, then guess what's going to happen? We're going to have infinite recursion, or in the Python case, after 1,000, it's going to stop. All right. And that's exactly the same as an infinite loop with whiles without incrementing the number up. So have a play with recursion. Be careful to put the end case in there. Otherwise, you'll get into trouble. And then start to think of what examples would we use recursion in programming. And I like to think of the ones where we've either got a graph-like data structure where we come along the next part of the data structure and we want to do the same thing to the next one and the next one and the next one. So we're sort of like traversing a graph like a map, or often we're sorting or going down a tree, searching for different things and returning the answer there. So have a play with that, see how you go. Make a note in the comments and just let me know how you went with recursion. Not an easy topic to understand, but a good one to learn. Thanks again, and talk to you next time.